Column-supported slab. Column-supported slab design concepts. This presentation provides the background of common practice in design of slabs that are supported essentially on columns. It starts by talking about ductile response of reinforced concrete because that is the basis of the design methodology, ductility. Then slab on common supports, talk about design options, serviceability and safety load paths, one-way and two-way floor systems, column-supported floor design practice, the strip method, which is most widely used, and the elastic response. Now let us start with the load deformation behavior of concrete, reinforced concrete. The force extension of common construction steel reinforcement is closely approximated by this diagram. There is a linear region, elastic response, and then there is a plateau plastic response. This is obviously idealized representation of the actual response. Concrete members reinforced with common rebar under increasing bending are assumed to respond like shown in figure 1. In effect, in its idealized response, once the reinforcement reaches its elastic limit, yield point, the section continues to deform under increased load with no additional deformation. I have to be more specific here. The member can possibly take additional load, but the section reaches a plateau. The phenomenon of undergoing deformation with essentially no increase in bending resistance is ductility. Now, this also applies to sections that are bending moment, rotation of reinforcement, or rotation of concrete reinforced with rebar is somewhat similar to the diagram at the top. Reinforced concrete is essentially ductile. It is designed as a ductile member and responds in that fashion essentially. Its ductility enables reinforced concrete to shed added load to where resistance is available. Like in this diagram, when load is increased, it will be resisted by the locations in the slab where reinforcement provides adequate strength. So the failure in this case in the common construction is somewhat similar to the diagram shown at the bottom. There will be hinge formations as selected locations, resulting in the collapse of the slab. Glass, on the other hand, is brittle. It breaks at the point where the strength limit is reached. Shatters, as shown here, doesn't shed the added load to where strength is available. Now, to ensure ductility of a concrete section, ACI 318 requires that the collapse in bending to be initiated by yield of tension reinforcement. Concrete itself is brittle, and if the section that I have shown here reaches its capacity by the strength of its brittle section, obviously the collapse will be immediate. So the design codes, such as ACI, make sure that the brittle part of the section, which is shown here, will not reach its limit before the section deforms substantially. How can this be achieved? By making sure that the reinforcement will yield before concrete reaches strength. Here on the right, I have shown the strain distribution across the section under bending. If the depth of the neutral axis is small, the strain at the bottom where steel is located will be larger. The smaller the depth of compression zone, the larger the strain in steel. By limiting this compression zone C, we can make sure that steel at the bottom will yield before the strain in concrete reaches the crushing of concrete. To ensure ductility, a concrete section, ACI 318 requires that collapse in bending be initiated by yield of its tension reinforcement. By limiting the depth of the compression zone relative to the tension zone, the extreme tensile strain can be controlled to reach the yield stress of steel before the extreme compression crushes the concrete. Now, this is the ratio stated in ACI 318, depth of compression zone over the distance to rebar to be less than 0.3. EC2 has essentially the same, provision. Now, the amount of rotation that a section undergoes before failure by crushing of its compression zone is measure of section's ductility. The smaller is the depth of compression zone, the more strain can be resulting in the rebar. the more strain in rebar, the more rotation. So there is a relationship between the ratio of compression zone to distance of the farthest rebar and the rotation. The amount of rotation is measured by this ductility, which is rotation at initiation of yield to rotation at collapse. And the relationship between the extent of the depth of compression zone and ductility is given here. The hatched region is the region that the codes generally permit. So you will have certainty that your design will be within the ductile limit of the code. As illustrated in the diagram, the smaller is the relative depth of compression zone, the larger is the rotation of the section. Diagram illustrates the range of the design options permitted by the major codes, and that is the yellow region that is permitted by the code. And the rotation of a section that can be sustained prior to failure. Now let us move to another aspect, the next step. First, I emphasized ductility. Now we come to design path. By that I mean how the load from its point of application is traveled, sustained to the supports of the member, travel of the load from the point of application to the supports. Consider this, the design of this single slab panel supported on 4 corner columns as shown here, loaded on at the center. Under low values of load before cracking of the slab, the response of the panel on the load is elastic response. The elastic response will have some deflection shape like what I have shown at the bottom right. The deflection contour is shown here for a homogeneous material. We assume the reinforced concrete for analysis as a homogeneous material. Now, the distribution of moment is somewhat similar to the distribution of deflection, similar in the sense that in this case the largest will be at the center. With increase of load and initiation of cracking, the development of resistance no longer follows the distribution B. Once cracking starts, then this will be disturbed because we no longer have a uniform homogeneous material. The panel relies on its availability and distribution of reinforcement. Once cracking starts, then the resistance depends on how much reinforcement and where the reinforcement is located. That is the load path which we as design engineers select for our work, as opposed to the load path which is determined by the elastic response. Once the elastic limit is reached, to sustain the load, the panel relies on the distribution of reinforcement. Then it is the reinforcement that determines how the load is carried to the support. In these diagrams, I have shown bands. Each band represents position of reinforcement. Here the reinforcement is positioned along the diagonal. Here it is positioned along both diagonals, and another option at the bottom right. Each strip marked in the three figures in plan includes one option of providing reinforcement to carry the load. In B, the entire load is carried by band located in one direction. Now in C, each of the diagonal reinforcement groups carry a fraction of the load. In the first, we had the entire by one direction. Here, each band carries a fraction. In D, the entire load is carried in one direction before it is shed to the bands in the other direction. There's a major difference between A, B, and C, and D. B and C had the characteristic of, especially C here, sharing the load. Here the entire is carried first before it is shared. Now we will discuss this concept a little bit further along. For its safety to carry the load, the panel relies on the distribution of reinforcement. Now here, figure B shows the elastic response, where the slab is, the entire slab is mobilized. In C, the entire load is carried by one group. In D, the diagonal reinforcement groups share the load. In E, the entire is carried in one direction before it is passed on to the other direction. D is a different concept. It is the failure by a yield line analysis. In other words, there will be hinges along the lines shown here. This type of failure is discussed in presentation 17. Presentation 17. In this presentation, the C, D, and E, and also B, are addressed. Now let me pause and draw your attention to what follows now. What is very important to recognize that there is a serviceability load path and a safety load path. The serviceability and safety load paths of a structure reinforced concrete structure is commonly not the same. They're different load paths. And before coming to the conclusion, I want to jump and say we will arrive at the conclusion that for serviceability, there is one load path. For safety, there can be multiple. So one and multiple options. Now let us look at serviceability and safety requirements using this propped cantilever as an example. This figure B, shows the force and reactions on the structure. You have reactions at the supports, and that is the applied load. This is the free body diagram. The outcome of the actions on the structure are shown by the elastic response in here. You will have a bending moment distribution as shown here, and these are the magnitudes of the solution using elastic response of uniform cross-section of cantilever, prop cantilever. The solution in C shows the deflection is used to calculate the deflection, used to give you the initiation of cracking. It gives you the vibration. These are the concerns of serviceability. So this diagram on the bottom right defines the service condition. And I want to jump ahead and say there is only one solution, one elastic solution, not more. So there is one service load or service condition diagram. The solution in C is commonly based on the linear elastic response of the uncracked section of the structure. That is what current codes, both major codes, ACI and EC2, use or permit using elastic linear of behavior and full cross-section. It is unique to the configuration and the load. By configuration and the load, I mean boundary conditions and supports and so on. The single solution is the basis of serviceability evaluation of the structure. It is commonly used to determine the deflection and initiation of cracks, as we had here before. Now, let us look at the safety of the structure. For safety consideration, the structural engineer comes into the picture. Before, we had the elastic response being the governing item. Here, the structural engineer is the initiator. The structural engineer selects a contiguous load path. It is the choice of structural engineer from the point of application of the load to the supports. In this here, I have shown two examples selected by the structural engineer, two different examples, two different load paths. Are the load paths limited to these two? Absolutely not. There could be many more. Look, here I have assumed the bending moment here to be 0.1 PL. This is different from the previous image, the previous page. The calculated bending moment based on the elastic response was different. But this is selection of the structural engineer. Here, another engineer assumes the moment to be 0.2 PL. Then, based on this assumption, we use statics and calculate the reactions. The reactions are different. But the structure satisfies the equilibrium, that is essential requirement. Number one, equilibrium of the loads must be satisfied. Statics. Both of them are in equilibrium. Then we draw the bending moment diagram which is arrived from the loads and reinforce the structure according to our own bending moment diagram. The moment diagrams will be different. The reinforcement will be different. The load paths are different. Are we limited to these two? No, there can be more. So in conclusion, for the safety of the structure, there can be many different options. There is not a single load path. For serviceability, there is one. For initiation of cracking, which is serviceability, there is one. But for safety, there can be many. So coming back here, for safety consideration of the structure, the structural engineer selects a contiguous load path from the point of application of the load to the supports. The load path selector gives the demand force for each member. Based on the load path you select, you calculate the demand. The demand in B is different from the demand in C, but each demand satisfies the selected load path. The structure is reinforced based on the calculated demand based here, calculated demand selected by the engineer. Figures B and C show two different engineer-selected load paths among the many options. Both options satisfy the required equilibrium of actions. The structure is safe, is reinforced accordingly. In summary, for service condition, there is one load path, namely elastic response. For safety, multiple options. The focus of the remainder of this presentation is, among many possibilities, to review the common industry and building code selected load path for safe design of column supported slabs. So what follows is what is recommended in the code is the prescriptive method of design outlined in the code among many possible options. This is the following. Now let us look at these diagrams one more time to first define one and two-way flow systems. This one and two-way flow systems is based on what is in the prescriptive method of the code. Before you start your column supported design, you have to define it as a one-way system or two-way system. And these diagrams are intended to illustrate this. The remainder of the figures show several options. These are several options. This is the applied load. There's a fundamental difference between B, C, and D. Between B, C, and D. As far as the code is concerned, a fundamental difference is defined. In C, the load is shared by the band. In D, the entire load is carried by the band in left-right direction, and the reaction P in up-down bands results in these to carry the entire P in up-down. So I want to emphasize the word entire. Entire in left-right, entire in up-down. That is where it leads to the design of column-supported floors in two times, once for the entire load in one direction and once for the entire load in the other direction, because this is the model used. In summary, in configuration D, for safe transfer of the load, once the system must be reinforced for the entire force in left-right, and once for the entire load in up-down direction. The arrangement D of providing resistance to the applied load is the basis of the two-way design of the column supported floors, which is the industry practiced. Now here we have an arrangement, floor slab reinforced with bonded tendons, orthogonal in both directions, once in one direction and once in the other direction, or orthogonal to one another, which is a two-way system. The arrangement of reinforcement governs the response and thereby the design of the slab as one or two-way system. The options for the arrangement of the primary reinforcement are: put it along the diagonal, that will be one way, and then you design it only once, or along the column lines, that is two ways, and then you have to design it two times. Use bottom and top mesh over the entire slab. That is the one way in the context of load sharing. That used to be in the past for reinforced concrete. A top and bottom mesh was used primarily for reinforcement. Positioning the reinforcement along the line of columns, namely two-way system, leads to design for full value of load in one direction, shedding the load onto the reinforcement in the orthogonal direction. In each direction, the reinforcement is designed to carry the full load. Now, the next screen provides additional explanation. Now, here we have a column-supported slab with a load shown here. The rebar can be placed along the diagonal. It shares the load between the intersecting members. Each reinforcement carries a fraction of the load. You design it only once for the load to be shared between the two. You decide how much of it goes along this diagonal and how much of it goes along the other diagonal. For safety of the structure, you decide. For the serviceability of the structure, the characteristics of the structure decides. Now, the one shown in C, rebar, now, along the line of supports, this is rebar along the line of supports, carries the entire load in one direction and passes it on to the bars in the opposite direction. So you have to design it once in this direction for 100% and once up down for 100%. Early on, before, well, many years back, 60, 70, 80 years back, that was more common. Mesh reinforcement was used primarily, a bottom mesh and a top mesh, primarily in non-prestressed reinforcement. Now, mesh reinforcement is essentially acts analogous to B. So you design it only one time to carry the load. The load is shared in two different directions from the point of application. Both ACI 318 and EC2 permit the design of floor slabs to be based on irrational approaches, following the principle of engineering mechanics. Why do I say this? I want to bring it up again, that you need not follow the prescriptive method described in either ACI 318, which is the strip method. You can use finite elements or use a top and bottom mesh over the entire, as has been done primarily before. Both 318 and EC2 include a prescriptive procedure, although both of them clearly permit using any other rational approach. The prescriptive procedure rests on the premise that the primary reinforcement is positioned along the line of columns. The prescribed arrangement of primary reinforcement leads to the strip method and two-way system. The general procedure comes in the next slides. Strip method is the outcome of two-way system. I am using this floor as an example. Highly irregular column supported slab shown will be used to demonstrate the design steps using the strip method. In this example, the columns do not line up and are not along an orthogonal array of columns. Here is the plan. You will select support lines along the line of columns and walls if they happen to be on the way. You identify support lines along the line of columns, and to each support line, you associate its tributary and conclude with a design strip. Here, I have the design strips identified in a left-right direction. You consider each of the support lines with its associate tributary as a design strip. In the basic strip method, each design strip will be analyzed, designed, and detailed in isolation based on the load directly on it. That is very important. In this method, if there is a load here where the cursor is positioned on the green design strip, it is assumed that the load is carried by this strip. It is not recognized that some of it will come to the blue, light blue, and in reality, it will be shared between the green and the blue. But that's a different story. As far as the method, prescriptive method is concerned, load which is on a given design strip will be carried by that design strip, will not be shared. The question of sharing is implicitly addressed when you go to the up-down design strips, because you later do the same in the orthogonal direction, once in one direction, once in the other direction. The other direction will take care of the item that I just raised. Figure shows the design strips in one direction. Each design strip is analyzed and designed for the load directly on it. A similar procedure will be followed for design strips in the orthogonal direction. Now, each design strip is looked at in isolation, extracted as shown here. Figure A shows one of the design strips extracted for analysis and design. For simple and common strip method of design, the extracted strip is considered along a straight line, even though you have a little break along the line. And again, the boundaries of the extracted strip are straightened. The preceding simplifies the analysis using software based on simple frame. So this will conclude or model or idealized like what is in the bottom before you go into the analysis. For each design strip along with a row of supports, one level above and one level below, as shown in the figure, is considered as the structural model representing the extracted design strip. This is the model for the design strip of the slab. It has rollers at the top, but no rotation. Rollers at the bottom, no rotation. But it is fixed in position here for stability. Far end the supports above and below are assumed rotationally fixed. The far end of the supports are assumed on rollers, except the bottom of the first support. You assume roller because you put post tensioning and you want the post tensioning to, so to say, create pre-compression in the slab, so they have to be on rollers. Generally, a simple plane frame software is used to analyze the extracted frame to determine the actions for design. For complex design strip geometry, possibly with beams, column drops, like here you have column drops, panels like we have here, beams, drops, panels as shown in B. Commercially available software is used. Otherwise, it's too complex to do it otherwise. So once each design strip is analyzed to determine the moments, here I show a fraction, a portion of the flow. Each span of each design strip, this is one span of this design strip, is divided into design sections. It is broken into these sections for evaluation of its design. The total value of the action on each design section is calculated. For each of these design sections, the distribution of action, such as moment, axial, is determined from the previous analysis, and the total value of that, the total moment, total shear, total axial is calculated. This is the integral of the distribution of the action, such as integral of moment, integral of the axial force. Using 318, this total, which is the total area, is applied to the total geometry of the design section to calculate a single representative, also referred to as hypothetical extreme fiber number, to be used for code check. If you want to calculate stresses, extreme fiber stresses, you apply this total to the total cross-section, and then you consider the cross-section like a beam section, and you calculate a single value. So the values that we use for the code allowable stresses are really do not relate to any specific point. These allowable stresses are derived from application of the total value of the integral to the total section. So they are more representative numbers of the state of the location. This is both in ACI and EC2. If EC2 is used, this preceding calculated value must be multiplied by 1.3 to compare it with the EC2 recommended thresholds for initiation of cracking or otherwise. Now here, presentation 7 explains why this is the case. An alternative option to the strip method today for extraction of the values is to use finite elements. That is an alternative method. Finite element by modeling and analyzing. Figure B shows the finite element discretization of the same floor. Finite element considers the entire floor in one model. You break it into elements, and then for each element you calculate the existing force, and you obtain a total deflection. It gives the elastic response of the entire floor, gives a more realistic picture of the floor's deflection for service condition, which is used for serviceability check. But when it comes to the safety check, we go back to what we had before. For safety check of the code, the common practice is to break the slab into design strips identically to the design strip method described earlier, and verify the adequacy through design sections along the design strips. So finite element helps us to obtain a better value for a closer value, I should say, for deflection, formation of cracking. But when it comes to safety, we go back to calculating the demands based on breaking of the slab into strips. It is now, besides that, it is permissible, ACI, and EC2, it is permissible to use this, the elastic solution, for safety check also, and determine the reinforcement, but it's not common because it's complex, as I will show in the following following slides. It is practiced when a bottom and top mesh are first provided, and where there is shortfall to bottom and top mesh, add rebar. The elastic response for safety, I have given it in this example. Rather than using strip method, elastic response has also been used as load path for safety. The slab is viewed as made up of small design elements. These will be the design element to be checked for adequacy. Demand for resistance of each element under the given load is determined generally using finite element methods. I'm going to jump ahead again here. Now, this only works, when I say only works, it is practical when you put a bottom mesh and a top mesh. And a bottom mesh and top mesh provide a base capacity everywhere. And then you check each of these elements from finite element against the base capacity. And where there is a drop in the base capacity, you put reinforcement. And typically, the bottom and top mesh are adequate, or you put enough reinforcement to minimize the added reinforcement beyond the mesh. Each design element is checked for reinforcement against the calculated demand at that design element. Then for each element, for bending alone, these are the actions. These are the actions for membrane action. These are the actions for bending and axial, which are calculated for each of these. Each element is considered subject to actions shown in B here. So this shows the in plane, this shows the in plane and bending moment. Each of these is subject to this. The local reinforcement of the design strip, the local reinforcement here is checked against the demand actions of the same element. Local reinforcement, local demand. In practice, the design starts by specifying bottom and top mesh over the entire slab. Reinforcement is added where the base mesh is deficient. The practice was more common in Europe and less common now. That brings me to the end of this presentation. And I started by emphasizing the ductile response leading to redistribution of demand to where resistance is available. Focus was on slab, on column supports. I talked about design options, serviceability and safety. I want to repeat myself. For serviceability, you have a one load path. For safety, you have a multiple load paths. Serviceability is not the privilege of the design engineer to decide. Load path and safety is the domain of the structural engineer's choice. The structural engineer decides what is the load path for safety. Then I moved to one-way and two-way systems. Two-way system leads to 2 times design in this structure, once along the line of columns in one direction, and then along the line of columns in the other direction. And then I focused on the strip method, which is the common prescriptive design method in major building codes. And elastic response model is also possible, used not frequently, because it leads to, in my opinion, in most cases, more reinforcement than the strip method. The material that I presented to you was extracted from the book which is shown on the right, and that brings me to the end of this presentation. Thank you for listening.